Okay, good morning, lads and ladies. Welcome back to college algebra. I want to open with an apology. I know that I canceled a bunch of office hours last week, and that's probably been rough on you guys if you've been looking for help or any sort of guidance. I've been very sick. Everybody in my family's been very sick, and we're starting to get over it now. Things are getting better. So no more of that shit, right? No more of that shit, I promise. We'll be back to the normal thing here starting today. So let's get into the swing of it. Last time we left off talking about linear functions, graphs of linear functions. We solved a handful of problems using and working with linear functions. Today, we're going to continue in that vein, starting to talk a little bit more about applications of linear functions. Still going to talk about rates of change and things like that, slope, and still plenty of equation solving and things like that. But the focus is going to be a little bit more on real world stuff and a little bit on trying to understand how quantitative measurements from the real world can be incorporated into algebraic statements, manipulations, expressions, stuff like that. So this is MAC1105, section 015, which is college algebra. And the date today is January 18th, 2022. The homework that came due today, I stripped a few problems from. You may have noticed that. They say that withdrawn by the instructor. Those were problems that used the linear regression function in the calculator. So we're going to talk about that stuff today. So main thing is just more linear functions, specifically applications. Linear functions. And specifically here, we're going to be talking about units and slopes. And remember, slope is the same thing as an average rate of change. One of our definitions of a linear function is that it has a constant average rate of change. That is, over any interval, you always get the same average rate of change for a linear function. And that average rate of change is the slope of the line, the slope of that linear function. Other things we're going to talk about a little bit more today. Let's see, we talked about points, so I'm just looking at my notes here. We didn't really get to talk about, I want to emphasize a little bit about horizontal and vertical lines, because these kind of live outside the normal way of thinking, at least vertical lines do. And also, and this was something that you saw in your last homework set, it's not terribly complicated, but I do want to talk about it a little bit, and that's parallel and perpendicular lines. And then, of course, yeah, regression, right? And calculator work. In addition to talking about linear regression, which is an important thing, I also just want to expose you a little bit to how to use this calculator. When I was younger, this was a really standard tool in high school algebra classes. Not that I made it very far in high school algebra classes. I think I told you guys I dropped out when I was like 15 after failing algebra 1 3 times. But even then, back in the late 90s and early 2000s, I got a lot of exposure to how to use these things. I think they're a little bit less common now, and I know a lot of us are either unfamiliar with or rusty with the calculator tools. So that's one of the things we're going to play around with quite a bit today. So if you have your TI-83, TI-84, please grab it out, right? Please have that along for the ride today. I do want to take just a quick peek at this next homework set to make sure I'm not missing anything here, any big topics. Mostly it's about units and linear regression. Yeah. Okay, good. Yeah, nothing crazy here. I think we've got everything in there. Let me just remind you some of the recipes that we're going to need here, right? So I'll say here, recall. Linear functions can always be expressed in the form f of x. Sometimes you'll see a y here, but when we want to talk about a function, we'll write f of x in place of y equals mx plus b, where m is the slope, which you can calculate as the rate of change. The rise over the run between any 2 points. Right, between any 2 points on the line. And B is the y coordinate of the y-intercept. The y-intercept is the point where the line, the graph of this linear function, hits the y-axis. All right. The other kind of formula I want to remind you of is the point slope form of a line. That point slope form is y minus y1 equals m times x minus x1. Or you could write this as f of x minus y1 equals m times x minus x1. Same thing, right? Again, y and f of x are interchangeable. The f of x just as a notation that emphasizes you're talking about a function. And here, x1 comma y1 is any point on the line. And m is the slope as above. Right, so these are the two kind of normal equations or expressions that we use to describe a line. There was a homework set that was due today. Sorry, I got a DM that I want to address. So homework 3 and quiz 3 were both due today, right? 1/18/22 at 9:30 a.m. If you do need more time on any of these, just send me again, send me a Canvas message letting me know, and I'll give you a late pass in, in my open math to go in and knock it out. No point penalty or anything like that, but please do send me that message so we can get it taken care of. Right, so linear functions or linear equations can be written in the form y equals mx plus b, or f of x equals mx plus b if you want to emphasize that it is a function f. M is the slope, which is the rise divided by the run between any 2 points on the line. So you can take your y-intercept and some other point on the line, or you can take just whatever 2 points on the line you know, and use those to calculate the slope. The rise is a difference of y values. The run is a difference of x values. And it's the same thing as the average rate of change. I should say this. I didn't want to put the normal notation for average rate of change in here, the f of b minus f of a over b minus a, because we're already using the letter b here to represent something else. But the rise is like f of b minus f of a, or y2 minus y1. And the run is like a b minus a, or an x2 minus x1, however you want to think of it. I think probably everybody is familiar with this in at least some sense. So that's all, just a recap. this point slope form is really more useful than this form, right? Some people call this slope intercept form. If you know the slope of your line and you know the y-intercept, then of course you can write down mx plus b. If you don't know the y-intercept, and we talked about this a little bit last Thursday, but you know some other point on the line, if you know the slope and some non-y-intercept point on the line, x1 comma y1, then you can write down the point slope form of the line. And of course, you can solve this for y and simplify it into mx plus b to find the y-intercept if you want. So really, I want you guys to get comfortable with this. It will make your life so much better. For example, one of the problems in your current homework set has you, so that problem, this problem right here gives you the slope and y-intercept. This problem right here gives you the slope and some other point, not the y-intercept. Now, could you take this and figure out the y-intercept? Yes, if you're patient, but you might make a mistake. It's so much better to take this information and plug it right into that point slope formula. So I don't want to solve that exact problem for you, but I want to show you how you can use this point slope form of a line to more easily solve those sort of problems. So let's start there. Our first example. Again, remember everything that I put here in the document camera needs to go into your notes. If you missed any of this, maybe now's a good time to take a screenshot. Otherwise, please just make sure you're writing this all down. Okay. So what we're going to do is we're going to find the equation for the line. And I'm going to use different values here with slope, let's say -2, passing through the point, how about -3, 7. Okay. You could draw a picture if you wanted to. Not a bad idea to do so, but I'm just going to attack this immediately and directly using my point slope form. You could try to figure out the y-intercept, right? You know the slope is -2, so every time you go to the right one, you go down 2. You could use that to get from this point to the y-intercept, but there's no reason to do that, and you might make a little mistake. So instead, just use the point slope formula. Point slope is just a more grown-up version of mx plus b. Your x1 is -3, your y1 is 7, and your slope m is 2. And that's all you need to plug into this. I'm just going to copy it down. If you're like me and you have a hard time memorizing formulas, like I love concepts in math, but I hate memorizing shit. If you want to remember a formula without just like drilling it in flashcards or something, every time you use it in a homework problem, write it down without the stuff plugged in. Just write down the formula and then plug in. And that act of writing it down each time you use it will really help you remember it. So y minus y1, okay, y1 is 7, so that's y minus 7 equals m, okay, m is -2 times x minus x1. And these parentheses are important. Don't forget these parentheses. This m really does need to distribute over both of those. So that's x minus, and what's x1? It's -3. So I'm going to write little parentheses -3 here like this. Now, when you go plugging a negative number into a formula, always good to put it in parentheses because this negative here is going to need to distribute, not distribute, combine. All right. So this, you could stop here for this problem because it just says find the equation. The homework problem I'm modeling this on, though, wanted you to get it into the slope intercept form, which is this form. So let's do that. The first thing I would do if I want to get this into like y equals mx plus b, is clean up the difference in here. So this is the same as y minus 7 equals -2 times. What is x minus -3? Can I write this in a nicer fashion?
X plus 3.
Yeah, very good, right? Subtracting a negative, same as adding. So this is x plus 3. Get myself a little divider there. We'll come back over here. The next thing I need to do, following my order of operations, right? I simplified inside the parentheses. It's your PEMDAS, right? There's no exponent. So the next thing I need to do is do this multiplication, right? This is the only place I have multiplication, and it's going over this parenthetical statement. So this -2 needs to distribute and hit each of these guys in here. So he's going to go wham and hit the x. He's going to go wham and hit the 3. The left-hand side is going to stay y minus 7. And I like to put these kind of bold double arrows. This means if and only if, or is logically equivalent to. This is y minus 7 equals, now distributing this -2, I get -2 times x, or just -2x, and then plus -2 times 3. Well, -2 times 3 is -6, so that's -2x minus 6. And that's looking better. The last thing we would do if I want to get this into f of x, or y equals mx plus b, is to add the 7. And I'll get y alone on the left. If I add 7 to both sides, -2x minus 6 plus 7. So -6 plus 7 is +1. And that's it, we're done. And in your in your work, as you solve problems, try to model the way I do things here. I know a lot of us kind of get into the habit of writing like a +7 here, or maybe down here, or maybe on both sides. Try to do things cleanly, right? Try to get to just the next step without cluttering the page up too much with extra notation. Any questions about what we did here? Okay. Notice that the slope is the same, right? Here's your mx plus b, right? Y equals mx plus b, or f of x equals mx plus b if you wanted. M is still -2, right? The slope is the same no matter what form the line is in. What is the y-intercept?
So
It's not 7, right? So the y value 7 is on the graph, but on the y-axis that's when x is -3. So look at this form, right? This is our mx plus b. Oh, I see it in the chat there. Yeah, the y-intercept is the ordered pair 0, 1. Very good. Or you could say 1, and I would know what you mean. If somebody asks what for the y-intercept, pay attention to the question. They might ask for an ordered pair. So we could say, B is 1. E, we're talking about the ordered pair 0, 1. Right, the y-axis is all the points in the plane whose x-coordinate is 0. The first coordinate of the y-intercept will always be 0, and that's why some people just say 1, because it's implied that this is a 0. But I like both of those answers. Those are both good answers. Any questions about what we did here, how we got to this, or how we got this information out? Okay, very good. Before we go further, I just want to remind you the next homework set and the next quiz, homework 4 and quiz 4, those are going to be due Thursday at the start of class. So remember the way we structure this, you guys have homework stuff due every day at the start of class. So make sure you get in and work on this stuff right away. Another thing we talked about last time we said that you can check if a table represents not just a function, but a linear function. By doing what? Who remembers? How do we, if I give you a table of values, how do you figure out if that table represents a linear function? You remember what we did?
Check the rate of change.
Yeah, like pretend this problem is one of those. I know it says something else, and we're going to come to this in just a second. But if I asked you to check if this was a linear function, then you would calculate the rate of change or the slopes between any two pairs of points here, right? So you could check the rate of change from 1 to 4, from 4 to 7, from 7 to 8, from 8 to 10, 10 to 12, and 12 to 14. If those all came out to the same number, then this would be a linear function. If any of those come out to be a different number than one of the others, then that would not be a linear function. So we said you can check if a table represents a linear function by calculating and comparing the average rate of change, i.e. slope, between all the consecutive points. If the average rate of change is always the same number, then, well, that's a function whose rate of change is constant. And by definition, that's a linear function. Then the function is linear. If any pair of slopes differ, right? If this doesn't happen, if they're not all the same, then the function is not linear. On the one hand, I do just want to remind you of this fact, right? It's something that I believe does show up in your current homework set again. But the real reason I'm bringing this up is because a lot of times in the real world, you get some data that is almost linear, right? Like you get a table with X and Y values, and you go calculating and comparing all of those rates of change or slopes. And maybe the slope is like 2 for a bunch of those points, but then it's 2.1 for one of those point pairs, and it's like 1.7 for another. It's not always constant, but it's pretty fucking close. You get some data that's not exactly linear, but it's close to being linear. And one of the things that mathematicians, specifically statistics people, really like to do is find the line that kind of best fits that data. What I'm going to say here is sometimes we get a table where all the average rates of change are close to one another, are close to constant, but not quite. This invites a big question. Can we find a linear function which, and I'm going to introduce some awkward terminology here. I'm going to say best fits such a table. Okay, I know this is a lot of words, but please do take the time to put it in your notes. I'm also going to draw a little picture here. All right, so maybe I have some data. This is going to be very qualitative, not very quantitative. Here's an example, right? This is not linear data. Okay, the slope from here to here is different than the slope from here to here is different than the slope from here to here is different than the slope from here to here is different than the slope from here to here. As always, this is my y-axis and this is my x-axis, and I'm not even going to give any numbers. All right, just think about the picture. So, kind of linear though, right? Kind of, like, I'm sure you see it. I see it. It's kind of all gathered around this line. It doesn't live on this line, but you know, there is a line here that appears to fit the data pretty well. And we can be really specific about which line that is, right? This one does not fit that data. This one does not fit that data. This or this does not fit that data. But this does. Now, what I mean by best fit is not like has as many points on it as possible. I actually don't care if this line has any of those points on it. What I mean is I want the distance between all of those points and that line, the vertical distance, to be as small as possible for all the points at once. So I'm going to do my best to draw in the line that I feel best fits this data. Something about like this, right? Maybe this isn't quite perfect, but like that. Yeah, that data is neatly gathered around that line. And what I mean by best fit is that the vertical distance, if you take all the vertical distances from these points to this line, and you add them up, the line that best fits this data would minimize minimizes the sum of all vertical distances from the points to the line. All right, so if I used any other line, I moved the y-intercept up or down, or I changed the slope at all, the sum or total of all those vertical distances would go up. So how do you find the line that makes all of those at once as small as possible? To handle this kind of barehanded, to solve this problem on your own without any technology is a pretty challenging Calc 3 problem. I went through the derivation. I go through the derivation when I teach statistics, and of course, very few statistics people have the calculus background to manage it. Nobody ever likes it, but but there are tools that do this for you. So the answer, I wouldn't talk about all this unless the answer was yes. And the easiest way to find that line is using the linear regression functiolator, regression function in your graphing calculator. So this is one of those times in the class, and there will be many others, where you need a graphing calculator. You need a TI-83 or TI-84. I'm going to show you how to do that now, right? So I'm going to take a specific table of data. I'm going to actually get some numbers, and we're going to find the line that best fits that data. Are there any questions about kind of the idea here? Okay. Really quick, I'd like to ask you a very qualitative question, no numbers. If that data was exactly linear, what would the line of best fit be?
A straight one?
Certainly a straight one, right? We're always, when we're talking about linear functions, they're always straight lines. But if all these points actually lived on a line, then the line of best fit would be the line that those points live on, right? That's kind of your perfect scenario. So a kind of sneaky second observation here is that if you have a table of values that you know are linear, right? You know the data is exactly linear. The linear regression function in your calculator is a cheap and easy way to get the equation of that line. So if the data was linear, then you can find the line that all those points live on using this regression function as well. All right, let me pull this guy up. So for those of you who are unfamiliar, what I'm using here is an emulator, kind of like a video game emulator. If you want to play N64 games on your computer, you can download an emulator. If you want to play with a TI-84, then you can download a TI-84 emulator. Obviously, doing it like this would work, but it's blurry as hell. It's not very good. So this works better. The first thing I'm going to do, and I want you all to play along with me here, turn this bad boy on. And then I want you to hit second and catalog. Second and 0 down here. You see in blue, it says catalog. The blue text above a button tells you what that button does if you hit this blue second button first. So if you hit second and then 0, it will open the catalog. And we're going to scroll down until we see diagnostics on. So these are all the functions in the calculator. All right, you see here, diagnostic on. I'm going to hit enter, and then I'm going to hit enter one more time. That's going to enable a tool that kind of measures how linear the data is. And we'll talk about that at the end. The other thing I want to do is talk about really quickly how to graph a function in this calculator. So if I, let me turn it off real quick. So if I want to graph a function in this calculator, the way I do that is by hitting the y equals button here on the left, and then typing my function in here. After I've typed my function in, I'll hit graph. And if I'm not happy with how that looks, I can hit this window button to change the viewing window, which is kind of like how much of the y-axis do you see and how much of the x-axis do you see. So let's start with a fun example here. How about like 7, and then this button right here is x, 7x plus 9. So this is a line with slope 7 and y-intercept 9, or 0, 9. I can hit the button graph here, and you see that line. If I'm not happy with this picture, if I want to see more or less of that graph, I hit my window button right here. And this is something you're going to need to get used to, is adjusting the viewing window. If you're not happy with how much of that graph you see, you can hit your window button there. X min tells you the smallest or leftmost X value that you'll see. X max tells you the largest or rightmost X value that you will see. So when you look at this graph right now, this X value over here on the far left is -10. And this X value over here on the far right is +10, because X min and X max are -10 and +10 respectively. X scale tells you how far apart the tick marks are. So right now that's set to 1. That means this is 1, this is 2, this is 3, this is 4. It means each tick mark is distance 1 apart from each other. And then the same thing for Y's, Y min, Y max, Y scale. That's the smallest Y value, or how far down you go on the graph. Y max is how far up you go on the graph, and the Y scale is 1. The -10 to 10 with scale set at 1, I'll call the standard viewing window. There are some other options in here. You don't need to worry about this shit. All right, so here's my graph of 7x plus 9. I can't quite see what's going on up here, right, at the y-intercept. So maybe what I'd like to do, I want to keep the x-intercept somewhere I can see it here. This isn't really a useful part of the graph, right? I can't see it. There's no part of the graph over here that I can see. So maybe I'll change my x min to something like -5. Leave everything else the same. And you see now it only goes over to the left here to -5. There also isn't anything over here that I can really see, right? So let me change my x max to +5, something like that. All right, now we're kind of zoomed in on the important part of the graph, but I want to see more up here. So let's change my y max. I want to be able to see higher. Let's change that to something like 15. And again, I'll hit graph. There you go. All right, so now you can see your y-intercept, you can see your x-intercept, everything looks pretty Gucci. The other function I want to show you, there's two other functions I want to show you here. There's this trace button. And when you hit that trace button, a little cursor shows up on the graph. And you can walk it around by hitting the left and right arrow keys. Now, you see it's using these weird decimals here. It's not giving me like the nicest numbers in the world, but you see right there, when x is 0, y is 9. That's because this guy, 7x plus 9, has y-intercept 9. If I wanted to try and find the x-intercept, I could again hit trace and walk this little guy over here until I'm close to the x-intercept. Now, what should the y value be at the x-intercept? Is everybody comfy with what I mean by x-intercept? This point right here where the graph crosses the x-axis? So just like where the graph crosses the y-axis, we call the y-intercept. Where the graph crosses the x-axis, we call the x-intercept. Sometimes we also call it a root. The y value there should be 0, right? Because the x-axis, all of the points on the x-axis have y coordinate 0. Like this point right here is 1, 0, where I'm circling with my mouse. This point right here is 3, 0. So if I want to know where my graph crosses the x-axis, I'm looking for the point where y is equal to 0. So you see where my cursor is right now, the little trace cursor. The y value is positive. It's like 0.808, which is not 0, right? It's a little bigger than 0. And since we go down as we go to the left, if I go to the left a little further, it should get closer to 0. That is 0.063. That's pretty close to 0. If I go left a little further, oh, it's negative now, negative 0.68. So somewhere between there and there is my x-intercept, right? And the trace function isn't going to tell me that exactly. It's just going to give me, I can hop around looking for it like this, which is fine. Looks like it's around -1.2, somewhere around there. The other function I want to show you, right? So that's graphing and using the trace function and changing your window settings. It's all very important stuff. There's also a way to use this to generate a table. So I have this function, y equals 7x plus 9, and maybe I want a table of values. You see above the graph button here, it says in blue, table. That means if I hit second and then graph, instead of drawing a graph, it will draw a table. So let's do that. Second graph brings up a table. Here we go. you can now use the up and down arrows to navigate through this table. And each one of these ordered pairs is a point on the line. So 2, 23 is a point on the line. 0, 9, we know that's the y-intercept, that's a point on the line. And if I start walking back, right, -1, 2, -2, -5, -3, -12, those are all points on the line. Okay. I think that's everything I wanted to show you with graphing, right? So you can draw a graph, that's important. Using the calculator to draw a graph is important. You can use the trace function to try to find points, specific points on the graph, but it's not going to be exact. So if you want to find those things exactly, you're going to have to do some paper and pencil work, and we'll talk about how to do that. But what we want to do right now is this stuff, right? We want to take a set of data and find the line that best fits that data. So let me show you how to do this. Okay, and I'll give us some data, some X's and some Y's. Let's do here. Yeah, let's do something like this. We'll jump up. Okay, that's enough. Oh. It is often the case that the data in your tables like this will be weird decimals, not super nice numbers. Because again, usually these things come from real world problems, right? Like I measure the height of a bunch of people and I want to compare it to their age, or I measure the fuel efficiency of a bunch of cars and I want to compare it to their weight. Real world numbers tend to be a little bit messy. We could graph this data, right? That's something we could do. But again, because the numbers are a little bit sloppy, drawing a graph by hand isn't going to be perfect. So let me show you how to do all this good stuff in the calculator. I'm going to hit clear. And then exit. Where's my exit function? I forget. Oh, quit. There it is. Second and then mode to quit. Second mode quit. Bring him back here. We turned the diagnostics on a minute ago. I'll remind you what that does. But before we do any of that, I need to bring up a table. So I'm going to hit math. All right, everybody. So I'm going to come back here. Sorry. Hit math, and then I scroll to the right one. Oh, sorry. Where is it? Oh. So I need to remind myself where the table function is. I thought it was in here. No, where's that shit? This is where we're going to go to do our actual regression. But I actually have to remind myself where to go to enter the table stuff.
Isn't it stat calc?
Ah, yes. Thank you. So stat. Yeah. Okay, thank you. So yeah, let's come back here. All right, nice clean. So what we're gonna do is hit stat and then edit. That's the first thing we're going to go to, and that's where we're going to enter our table. So let's put this in our notes. Steps. So stat, and then select edit, hit enter, and now you've got lists. They call them L1, L2, L3. You put your X values in L1, and you put your Y values in L2. If you jumble those up, you can change it. There's a way to do it, but that's the default. So you put them in order. So first, -1.3. Make sure you use this button down here for the negative, not the minus button here. This is like the subtraction operator. This is like the negative symbol, and your calculator understands those as different things. So when you enter a negative, always hit the negative down here. All right, -1.3, and then next was -0.5. And then next was +0.25. I always like to put the zeros ahead of the decimal. Then +1.3. Then +2.17. All right, so there's my X values going into L1 or list 1. And then in L2, across from each X value, you're going to put the associated Y value. So across from -1.3, we're going to put -2. Across from -0.5, we're going to put -1.2. Across from +0.25, we're going to put 0.7. Across from 1.3, we're going to put 2.1. And across from 2.17, we're going to put 3.14. Right, there's my lists. And in order to find the line that best fits these, your next step, again, you're going to hit stat. And then you're going to scroll right to calc. I'm going to scroll right to calc. And then you're going to scroll down to, in this it's item 4, it'll always say lin reg. May say AX plus B, may not. I think the 84 always says AX plus B. I don't remember what the 83 does. And then hit enter. So over to calc, down to linreg, enter. Some calculators will do this, others will not. The TI-83 assumes you put the X's in L1 and assumes you put the Y's in L2. If you want to change that, this is where you can change that. Don't worry about any of the other stuff. Just make sure your X's are in the right place, your Y's are in the right place, and then you come down to calculate and hit enter. So check the X list and Y list are correct. Scroll down to calculate. Hit enter. All right. And it's going to generate several things. A, right? So this says Y equals AX plus B. This is the output. A is your slope. B is your y-intercept. So the output says y equals x plus b, and then it will say a, and I'm just going to round to 3 decimal places here, 1.548. B is negative 0.047. Again, rounding at that 3rd decimal place. And then it also gives you these numbers r squared and r. I'll explain what these are. These are the things we're getting from the diagnostics. R squared here, again, round to 3 decimal places, 0.983. And R is 0.991. Okay. The R squared and R, these are the numbers that we're getting since we turned on that diagnostics feature. Like I said, I'll talk about what these are in just a second, but first, let's talk about this stuff. So what this means is that the line that best fits our data, the line we're looking for, is y equals ax plus b. Well, a is 1.548. So that's 1.548x plus b is negative 0.047. Right? Or you could write this as y equals 1.548x minus 0.047. So the slope is about 1.5. And the y-intercept is about negative 0.04 or negative 0.05. Okay. Really quickly, if I hit y equals here, and I throw that guy in, 1.548, and then again, this button up here for x, minus, I'm subtracting now, so I use the minus rather than this negative button, 0.047, you can see your line. And my window settings are still what they were before. I'll change this back to the standard ones. Right. It looks like the y-intercept is 0, but we know it's not. It's just very close to 0, but it is a negative small number. There is also a way to get the data to show up in here. I think we hit second and then here to go to stat plot, and you can turn plot 1 on. Let's see. Enter. And then this tells me to give a scatter plot. X is in L1, Y is in L2. And I'll use little pluses for the points themselves. So that looks a little better. Here we go. All right, and if we want a better picture of this, we can zoom in by changing our window settings. Maybe I'll go, my X values were all quite small, right? From negative 1.3 to 2.17. So I change my values to something like negative 4 to 4, something like that. My Y's were also quite small, ranging from negative 2 to 3.14. So I'll do that also negative 4 to 4. And there you see, right? So this line doesn't go through any of those points. That's the first thing I want to indicate here. The line of best fit doesn't touch any of those points. We're not trying to find the line that passes through those points. We're trying to find the line that gets closest to all of them at once, which is very different than saying like passes through the most of them or anything like that. Okay, very good. Any questions on this procedure to get our regression line? That's what this is called. The line of best fit is the regression line.
How did you change it to the scatter plot again?
So if we wanted to add in the scatter plot, you see in blue up here above y equals, it says stat plot. that's the function we want. So hit second and then y equals. You can enter a bunch of stat plots. I just hit enter on stat plot 1. I can turn it on or off here. If I wanted to turn it back off, this is what I would do. I would select off. You can tell it that you're looking for a scatter plot or a line graph or a bar graph. We want a scatter plot. We don't need any of that other stuff. Your X's are in L1, your Y's are in L2, and then you can change the little mark. So I'm going to change this back to the square and do that. All right, but I think the little X is better. You don't need to use the stat plot function in this class. You do need to know how to get the regression line. The stat plot function is nice though. I think it does help you see the picture and understand what's going on.
Thanks.
Yeah, sure, of course. Any other questions about what we did with the calculator here?
I have a quick question.
Yeah.
So after I put in my like my stuff, whenever I press graph, it just doesn't show up like at all. Like my graph is just completely bare. But whenever I press stat and edit, it shows that I put everything down.
So in order to get the line, I had to come to, remember to graph any function, you got to hit y equals and type the function in. So go ahead and hit y equals and make sure you've typed in this equation for y1. y1 equals 1.548x minus 0.047. And that should get you the line. If you want to see the little points themselves, the data points, we need to turn on the stat plot feature by hitting second, y equals, selecting this first guy, and it'll probably say off. And you just scroll over here to on and hit enter. Then you should get both.
Okay. Thank you so much.
Yeah, of course, of course. Anybody else having a hard time getting the calculator to do what they want? Let's see something in the chat. So Brent is seeing the error dim mismatch, which means dimensional mismatch. Go ahead and look back at your lists and make sure that you have everything arranged just like this. So you need to have the same number of things in L1 and L2. Maybe one of those didn't get put in. It means that you have an extra dimension, or you're missing a dimension in your data somewhere. Probably one of the X's or Y's is missing. Let me see what happens if I clear this out, hit enter, where is it, delete. I delete one of those and then I hit graph. Yeah, I get the same error, right? So we need to just come back into stat, edit, enter, and then make sure everything matches here. So cross from negative 1.3 should be -2, negative 1.2, then 0.7, 2.1, then I don't know. Sorry, trying to use keyboard shortcuts. All right, and then it should work. Again, you won't get the line until you type the line in here. So anytime you want to graph any function, you have to go to y equals and then type it in. It will not graph the line automatically. Okay. So these are the data that you need, or the information that you need to get the line of best fit, right? And this would be the answer for our question. Final answer, done. These guys tell you how good a fit that line is. So R is called the Pearson correlation coefficient. And it is a measure sort of how close to linear your data are, data is actually a plural. If R is very, very close to 1, the data are very linear. And have positive slope. In statistics, we call this a positive correlation. If R is very close to 0, the data are not at all linear. Maybe you just have a random cloud of points, right? That would be R equals 0. And if R is very, very close to -1, the data are very linear. And have negative slope. And it's really R that we calculate, that we think about usually. R is always a number between -1 and 1. If R was exactly +1, that means that data is exactly linear, like actually lives on a line, and that line is positive slope. If R were exactly -1, that would mean the data are exactly linear, and that line is negatively sloped. R squared is just another tool for measuring linearity, but since you square, right, this number is literally the square of this number. Take this number, multiply by itself, you get this. Squaring R just makes it positive, right? So if R squared is really close to 1, then your data is very, very linear. Okay. Any questions about any part of this linear regression stuff?
I have one more quick calculator question.
Yeah, please.
I think my original line that we drew on the calculator is also still on my scatter plot. How
Oh,
the
yeah.
heck do I move it?
So if we want to get rid of something, go ahead and hit Y equals and delete whatever you have in there, right? So if I could plot something like X squared. And if I have two different equations in here, you'll see the two graphs, right? I don't want the parabola, so I would just come back here and delete that second one by scrolling down to it and hitting clear.
Perfect. Thanks.
Happy to do it. Okay, any other calculator questions? I know this stuff is a little bit tricky. Okay, we'll play more with the calculator through the semester. But changing your viewing window, very important. Knowing how to graph a function in the calculator by typing Y equals, entering it, and then hitting graph, very important. The last thing I want to talk to you about today are units, units of measurement. And something called dimensional analysis, which sounds fancy, but I promise it's not that fancy. We all know what a unit of measurement is, right? Like if I measure my height, if I were to tell you my height is 215, then you'd be like, whoa, shit, that guy's 215 feet tall. I'd be like, no, 215 centimeters, like 2 meters tall. The units of measurement are very, very important when you're reporting any measurement. So, for example, doesn't really make sense. unless I tell you 215 what? 215 feet is huge. 215 centimeters is about 6 feet. Right, just over 2 meters. 215 miles. I'm not 215 miles tall, of course, right? But the units are the things that you're using to measure, right? They're kind of standard understood lengths times whatever. You can do algebra with units. Also, each unit has an abbreviation, right? For feet, usually you'll see FT, centimeter. Usually you'll see cm. There's lots of these. Obviously, I can't describe all of them, but some other common units. The meter, which we just write M, right? And a meter is about 1 yard, about 3 feet. The foot, obviously, we've mentioned there. Miles. And this, we don't, some people abbreviate this as MI. The second for time is usually just S or sometimes SEC. The liter, this is a unit of volume. This is usually just written as L. What other common stuff do you guys run into? Maybe I'll just leave it as this, right? So sort of the cool thing here and what dimensional analysis is all about is this fact that you can do algebra with units. Basically, you can treat units like variables. For example, if I take M over S, right? M is for meters, S is for seconds. Meter over second, or meter is always the plural, over seconds. This has a particular meaning. If you discuss some distance, right, which is so this is a distance, and you divide it by a time, where else have you seen something like that? Next time you get in your car, look at your speedometer. It'll say MI divided by H. That's miles per hour. The division bar can be thought of as the word per, right? Like if I have $100 and I want to divide it up among my 10 best friends, that would be $100 divided by 10 friends, or $10 per friend, right? The division bar and the word per in English mean the same thing. So if you take a distance and you divide by a time, like meters per second or miles per hour, this is a speed. Okay. Or I could talk about the units of kiloliters. The prefix K stands for kilo or 1,000 of, like km is kilometer. KL would be kiloliters. This would be kiloliters per mile. Sorry. Oh, sorry. This would be a strange unit, but the reason it comes to mind for me is because they're doing some road work in front of my house and they're laying down a bunch of gravel and asphalt. Well, the amount of gravel that they're laying down, that's a volume. It's a large volume. So it would be measured in thousands of liters. And they have to use some amount of that gravel for every mile of road, right? So the units here, kiloliters per mile, would be a volume divided by a distance. Now, this doesn't have a special name. So for example, the amount of gravel needed to construct a certain length of road. Understanding units and specifically ratios of units is a big deal. The main place this is going to come in for us is when we talk about slopes of linear functions, right? Or rates of change. Rates of change are fractions, right? A rise over a run. So if your rise or your y values are measuring a distance and your run or x values are measuring a time, then your slope is a speed. Cool, right? So slope has units. If the input and output, the x's and y's, have units. And in every real world problem, inputs and outputs always have units. They're never just numbers, right? Maybe it's a time, maybe it's a distance, maybe it's something else, but there's always some sort of unit. And these can be a little bit funny, right? Like this last one, this is kind of a strange unit. It's not something you're gonna think of right away. In physics, you'll encounter a lot of this stuff too. Like you could have, I don't know, the measure of charge, coulomb, right? You could talk about coulombs per square foot. And that's like the amount of charge distributed on some charged object, like a piece of metal. Lots of stuff like that. So slopes or average rates of change have units which come from the units of the associated function. I'm going to draw a picture here, and this picture isn't going to be a linear function, but of course it could be. I'm just going to draw a sort of standard function, an arbitrary function. All right, so here's the x-axis. This is y equals f of x. And maybe my function looks something like this. The units of x could be lots of things. A common one would be like time in seconds. And the units of y, the units of the output, could be, let's say, let's pick a silly unit. What sort of silly units do we have in the homework? miles, pounds. Well, okay, sure. All right, so the output of my function is measured in pounds. The input of my function is measured in seconds. Those are the units associated with each of those. So each y value here is a weight in pounds, and each x value here is a time in seconds. So let's say here I have the point 3, 1. And maybe over here, I have the point 10, 4. So this x value is 3, this x value is 10, this y value is 1, and this y value up here would be 4. If I want to find the slope or the average rate of change for this function, we can do that. The average rate of change for the function f of x from x equals 3 to x equals 10 is, again, just following our formula, f of 10 minus f of 3 divided by 10 minus 3. Right, this up here is your rise. This down here is your run. So what is f of 10? F of 10 is what? Now we're just out of time here, so let's wrap this up quickly. What is f of 10?
4.
4, very good. And what is f of 3?
1.
Very good. This is 4 minus 1 divided by 10 minus 3 is 7. But here's the big point. That's 4 pounds minus 1 pound. The top here is measured in pounds, and the bottom here is measured in seconds. So altogether, this is 3/7, 3/7 pounds per second. So whatever this thing is measuring, it's measuring the weight of something over some time. That weight is increasing by 3 pounds every 7 seconds, or 3/7 of a pound per second. So the object whose weight is described by the f of x is increasing at 3/7 of a pound every second. Now this is on average, because it's an average rate of change. On average, from time x equals 3 seconds to x equals 10 seconds. Right, and this thing down here, we would call an interpretation of the slope. The average rate of change. And I will ask you from time to time to calculate and interpret rates of change. And it's important that you know how to do that. It's really just about understanding the units, right? And saying 3 pounds over 7 seconds is the same as saying 3/7 pound per second. In other words, 3/7 of a pound every second. So this is all I really wanted to say about units. You can imagine how this can combine with the linear regression stuff we were doing. So if you had a bunch of data, you wanted to find the line that best fits that, the slope would have the units of y over the units of x. And this is what I'll close with. So the average rate of change, the units of slope or average rate of change will be the units of the output or y values divided by the units of the input, the units of the x values. And that will give you a new unit. All right. So that's it from me for today. Please do wrap up that new homework set. I believe it is homework 4 and quiz 4. Those will both be due for you at the start of class on Thursday. So you want to work on it today, work on it a little bit tomorrow. You don't want to be trying to crunch this out Thursday morning. So please, today and tomorrow, homework 4, quiz 4. Next time, we're going to talk about absolute values, and then you'll have over the weekend to work homework 5 and quiz 5. We may start talking a little bit about quadratic functions. We may wait till next Tuesday to do that. Depends on how much time it takes to get through the absolute value stuff. This is where we're going to leave it for today. If you have any questions, I do have an office hour right after this. Otherwise, I'll see you guys on Thursday, okay?
Real quick, can I take a screenshot of the notes?
Sure.
Thank you. Thank you. Have a good day.
Of course. You too.